Welcome back, students. Let's resume. Here is a grand summary of everything that is important from the previous lesson video segment. You're looking at the definitions of sine, cosine, and tangent, the three standard trigonometric ratios, defined as opposite over hypotenuse, or y over r, vertical over radius, adjacent over hypotenuse, or x over r, horizontal over radius, and finally opposite over adjacent, y over x, or vertical over horizontal. Here the angle theta is the center angle, or if you just focus upon the red triangle alone, then this is lower left hand side corner angle, and right angle is on the right hand side. The top angle is going to be its complementary angle. Now how about the other trigonometric ratios, cosecant, secant, and cotangent? They're just obtained by flipping up sine, cosine, and tangents respectively, so they are nothing more than reciprocals. Okay, so much for review, and let's go over to the next topic, and the next topic as briefly as possible, and then let's begin some examples. Now, here is the formula. Here is a set of formula for complementary angles. Pi over 2 minus theta, pi over 2 minus theta, pi over 2 minus theta. In that case, we have some relationship between sine and cosine. Now, if you try to memorize this set of formula, it's going to be rather complicated. Here is my suggestion. Use picture. Now, here is a right triangle, and let's say A is the standard angle, and B is not in standard position, but it can be made into standard position by flipping and turning. Now, A and B add up to 90 degrees. Why? The R over here is right angle, 90 degrees, and then the sum of the internal angles of triangles must add to 180 degrees. And 90 degrees already there, so this adds up to 90 degrees. Now, let us express them in radian measure, and we're going to need some different characters, some different notations. So let me use Greek letters. Alpha as this radian measure here, beta as radian measure over here. Then we have alpha plus beta is pi over 2. Consequently, beta is pi over 2 minus alpha. That's a relationship between angle B from angle A. Now, just looking at this, sine of beta here is opposite of hypotenuse of this angle here. What's the opposite? X. Hypotenuse is, of course, R. Now, if you look at it from this angle here, alpha, then that's the same as adjacent over hypotenuse. So these two are the same. Sine of beta and cosine of alpha are the same. How about cosine of beta here, from here? Cosine of beta, so adjacent over hypotenuse. What's the adjacent? It's y. So what do we get? Y over r. Now, if you look at it from this angle here, y over r, that's opposite of hypotenuse, that's sine. One more, tangent of B, or tangent of beta over here, opposite over adjacent, that's x over y. And if you look at it from angle A, then that's adjacent over opposite, so that's cotangent. And then we end up with this result. Sine of pi over 2 minus alpha is equal to cosine of alpha. Cosine of pi over 2 minus alpha is sine of alpha. Final tangent of pi over 2 minus alpha is cotangent of alpha. And of course, you can extend this idea to arbitrary angle, and we end up with this result. How do you expand this into arbitrary angle? Well, to tell the truth, arbitrary angle is something we're going to discuss next week. Obtuse angle and further angle, negative angles, and so on. We have explanation only for acute angle, but luckily it works out just fine. Okay, just one more before going through some further example. All right, As a matter of fact, you can consider this as an example too. Trigonometric values of basic angles. Here is one basic triangle. What is this? It's an equilateral triangle. We have three sides, 2, 2, and 2 units. And then the angle, 60 degrees, 60 degrees, and 60 degrees over there. But then again, what did I do? I took a bisector of the top angle and then divided this equilateral triangle into two right triangles with the angle 30 degrees and 60 degrees and 90 degrees. And do you remember that bisector of the top angle divides the base side equally and perpendicularly? Bisects equally and perpendicularly. Consequently, we have this right triangle here, 60 degrees and 30 degrees. And then this is 2 units. This has to be half of 2 units, so it should be just 1 unit. If you use Pythagorean identity, then you're going to end up with square root of 3. What do you mean by that? Hypotenuse squared is equal to 1 squared base plus height squared if you don't know the height. And consequently, height squared is 4 minus 1, which is 3. So height has to be square root of 3. And you can find out height like that. Now, if you're good at geometry, you want to deduce like this. But most students would feel much more comfortable just by memorizing the picture. You get 1 square root of 3, 2 triangle with the angles 30 degrees and 60 degrees. In terms of radian measure, it's pi over 6, pi over 3, and pi over 2 instead of 30 degrees, 60 degrees, and 90 degrees. And that gives you nice trigonometric angles here, which will be represented here and then also down here. Shall I show you? Okay, I'll show you first. That's how you get sine, cosine, and tangent value of the angle pi over 6. Well, we have x value as square root of 3 and y value as 1 and r value as 2. So this is opposite of hypotenuse, so 1 over 2. This is adjacent of hypotenuse, so square root of 3 over 2. And this one is opposite over adjacent, so we have 1 over square root of 3. If I flip this triangle and make it stand up, you have this picture, 1, 2, square root of 3 triangle, and sine is now opposite of hypotenuse, so square root of 3 over 2. Cosine is 1 over 2, and tangent is square root of 3 over 1. Just remember the definition and put this picture with all those lengths and angles into this circle and you can easily deduce them. Here's another picture. This time it is 1 square root of 2 triangle, and this is right isosceles triangle. 90 degrees, 45 degrees over there, 45 degrees over there. So we have the isosceles triangle. This and that length must be the same. So let's take 1 and 1. Use Pythagorean theory and you get square root of 2 here. And that's how you get trigonometric ratios for this case, 45 degree case. Just inscribe 1 square root of 2 triangle at 45 degrees or pi over 4. And what do you get? Sine as opposite of hypotenuse and cosine as x over r. So we have 1 over square root of 2. And tangent y over x is 1 over 1. And there are more special cases. A degenerate triangle here, 0 degrees, so you don't have triangle. So what do we have? Y is 0, nothing vertical. Cosine is 1 because radius and x are the same. So let me write this one as y over r, which is 0 over 1. So that's 0. And cosine of 0, what is that? Cosine of 0 is x over r, which is 1 over 1, so it's 1. And how about tangent? It's y over x, and then y is 0, it doesn't go up at all. And that's 0, you can calculate like these. Degenerate triangle. Finally, we have another degenerate triangle. 90 degrees. So we just have vertical line segment. Sine is 1. The reason is because sine is y over r, and horizontally, vertically, vertical and the radius is the same. So we have that. How about cosine? Horizontally, I don't go anywhere. So 0, so this is x over r. So this is 0 over 1, which is 0. How about tangent? This is y over x, isn't it? Vertically goes up by 1, and horizontally 0. Hey, wait a minute, what is 1 over 0? That's undefined. So tangent is undefined at theta equals to pi over 2. They all come from the degenerate triangle. Let me show you everything from the beginning. Okay, here we have a standard 1 square root of 3, 2 triangle, 30 degree, 60 degree, 90 degree, or pi over 6, pi over 3, pi over 2. Next, 45, 45 degree, 45, 45, 90 degree triangle, 1 square root of 2 triangle, or pi over 4, pi over 4, pi over 2 triangle. And let's begin with smallest to largest. Sine of 0, angle 0, so I don't see anything going up. So we have degenerate triangle, which is actually a line segment here. Vertically, no, nothing, so 0. Horizontally, everything, so r over r. Tangent, vertical or horizontal. Vertically, nothing there, so that's 0. And then if we inscribe 1 square root of 3, 2 triangle appropriately to 60 degrees or pi over 6, you get this result. Next, 45 degrees, so let's put 1 square root of 2 triangle and inscribe those into unit circle, and you have all these results. One more, this time 60 degrees, so 1 square root of 3, 2 triangle again, but in a little bit different position, standing up position. And just by looking at all those ratios, you get all those trig values. Finally, the degenerate triangle, again, 90 degrees, so line segment just goes up. And horizontally, I go nothing, so x is equal to 0. And that corresponds to this result and also that result. The last one can be a little bit tricky, and it's going to be particularly so if you look at the graph. Thank you. That's where I'm going to stop, and we're going to do some example problems in the next video segment.